Could a galaxy exist without dark matter? The short answer is yes, it seems so. We think we've found a few. But that simple answer hides a much bigger, more complicated story. It's a story about a mystery that has puzzled scientists for almost 100 years. It's about how we know what we know about the universe, and it's about how one weird discovery can flip our understanding of everything on its head. To get why a galaxy without dark matter is such a big deal, you first have to understand why we think dark matter is a thing at all. It wasn't an idea someone just came up with for fun. It was a conclusion forced upon us by looking at the sky and realizing that what we see doesn't make any sense. The universe isn't behaving the way it should. It started a long time ago, back in the 1930s. An astronomer named Fritz Zwicky was looking at a giant group of galaxies called the Coma Cluster. A cluster is just what it sounds like, a city of galaxies all held together by gravity. Zwicky was a bit of a character, famously difficult but also brilliant. He was measuring how fast the individual galaxies in this cluster were moving, and he found something that shouldn't be possible. They were moving way, way too fast. Think about it like this. Imagine you have a ball on a string and you're spinning it around your head. The string is what keeps the ball from flying off. The faster you spin it, the stronger the string needs to be. Gravity is the string that holds a galaxy cluster together. Zwicky looked at the galaxies in the Coma Cluster and calculated their speeds. Then he looked at all the stuff he could see, all the stars and gas in those galaxies, and calculated how much gravity they should have. The numbers didn't match up. The galaxies were moving so fast that the gravity from the visible stuff wasn't nearly enough to hold them. The cluster should have just flown apart millions of years ago. The string wasn't strong enough for how fast the ball was spinning. Zwicky's conclusion was bold. He said there must be a huge amount of invisible stuff in the cluster. It's something we can't see, but something that has gravity. He called it Dunkel Materie, which is German for dark matter. For a long time, not many people paid attention. It was a weird idea, and the measurements were hard to make. Maybe he just got it wrong. But then, in the 1970s, another astronomer came along and found the same problem, but somewhere else. Her name was Vera Rubin. She was looking at individual galaxies, not clusters. Specifically, she was looking at how they spin. You'd expect a galaxy to spin like a solar system or a merry-go-round. The stuff in the middle, where most of the mass is, should move fast. The stuff on the outer edges, far away from the center, should move slowly. Mercury zips around the sun, while Neptune crawls along. That's just basic gravity. The farther you are from the central mass, the weaker the pull and the slower you go. Vera Rubin pointed her telescope at the Andromeda Galaxy, our nearest big neighbor. She measured the speeds of stars and gas clouds at different distances from the center. And she found something impossible. Again, the stars on the outer edge of the galaxy were moving just as fast as the stars near the center. The galaxy's rotation curve, a graph of speed versus distance, was flat. It didn't drop off like it was supposed to. It was like Neptune was moving at the same speed as Mercury. That just doesn't work. For that to happen, the string of gravity has to be just as strong way out on the edge as it is in the middle. But that's not where the stars are. The visible light of a galaxy fades out. Most of the stars are packed into the central bulge. So, where was all this extra gravity coming from? Rubin and her colleagues studied galaxy after galaxy. And they all did the same thing. Every single one was spinning too fast. The flat rotation curve was everywhere. It was undeniable. The conclusion was the same one Zwicky had reached decades earlier. Galaxies must be sitting inside a giant invisible halo of stuff, a halo of dark matter. This dark matter doesn't shine, it doesn't reflect light, it doesn't block light. It seems to do nothing at all except for one thing: it has gravity, and there's a lot of it. The calculations show that for every 1 pound of normal matter, the stuff that makes up you, me, the stars, and the planets, there are about 5 pounds of dark matter. The universe we see is just the tip of the iceberg. About 85% of all the matter out there is completely invisible to us. This was a huge shift in our understanding of the cosmos, and more evidence kept pouring in. Take gravitational lensing. Einstein told us that massive objects bend the fabric of space-time. A beam of light traveling through space will follow that curve. So a huge object, like a galaxy cluster, can act like a lens, bending and magnifying the light from a galaxy sitting behind it. We can see this happen. We see the light from distant galaxies stretched into weird arcs and smeared into multiple images. Here's the thing. We can use those distorted images to calculate how much the light is being bent. And that tells us how much mass must be in the cluster doing the bending. And every time we do it, we get the same answer. There's way more mass, way more gravity than we can account for with the visible stuff. The amount of lensing we see perfectly matches the amount of dark matter predicted by the speedy galaxies inside the cluster. It's a completely independent piece of evidence pointing to the exact same conclusion. The most famous example of this is the Bullet Cluster. This is actually two galaxy clusters that have smashed through each other. It's a cosmic car crash. When they collided, the normal matter, which is mostly hot gas, slammed into itself and slowed down, kind of like a massive traffic jam. We can see this hot gas using X-ray telescopes. It's sitting right in the middle of the mess. But when we look at the gravitational lensing from the Bullet Cluster, it tells a different story. The map of the mass, the map of where the gravity is strongest, isn't in the middle with the hot gas. It's on either side, having passed right through the collision without stopping. The galaxies themselves, which are mostly empty space, also pass right through. But the lensing shows that most of the mass is with the galaxies, not with the gas. This is the smoking gun for dark matter. It shows that the normal matter, the gas, and the invisible matter can be separated. The dark matter just sailed through the collision without interacting at all, just like a ghost. Normal matter crashed and burned. Dark matter didn't even notice. This observation is incredibly hard to explain without some kind of invisible, non-interacting substance. And there's more. We can look back in time to the very beginning of the universe. We have a baby picture of the cosmos called the Cosmic Microwave Background, or CMB. It's the leftover heat from the Big Bang. It's an almost perfectly uniform glow across the entire sky. But there are tiny, tiny temperature fluctuations in it, little hot and cold spots. These little spots are the seeds of all future structure. The slightly denser, slightly cooler spots had a little more gravity, and over billions of years they pulled in more and more matter to form the galaxies and clusters we see today. We can run computer simulations of how the universe should have evolved from that baby picture. And the only way to get from those tiny seeds in the CMB to the massive cosmic web of galaxies we see today is if there was a huge amount of dark matter. Normal matter, the stuff made of protons and neutrons, interacts with light. In the early universe, it was pushed around by the intense radiation. It couldn't clump together easily. Dark matter, on the other hand, doesn't care about light. It starts clumping together right away, creating deep pockets of gravity called dark matter halos. These halos then acted as gravitational scaffolding. After the universe cooled down enough, normal matter could fall into these pre-made dark matter pockets and begin to form stars and galaxies. Without dark matter, there simply wasn't enough time for gravity to form the huge structures we see. The universe would look completely different. It would probably just be a thin, uniform soup of gas. So, for all these reasons, dark matter became the standard picture. Galaxy rotation curves, cluster dynamics, gravitational lensing, the structure of the cosmos itself. Everything pointed at this invisible stuff. It was the glue holding the universe together. The idea became so entrenched that the existence of a galaxy without dark matter felt like finding a fish that could live without water. It just didn't seem possible. Every galaxy was supposed to be born inside one of these dark matter halos. It was a fundamental ingredient. And then, a few years ago, a team of astronomers built a new kind of telescope. It wasn't a giant mirror, it was an array of telephoto camera lenses, the kind a photographer might use. It was called the Dragonfly Telephoto Array. Its design made it exceptionally good at seeing very faint, diffuse things that other telescopes might miss. A team led by Peter von Dockum at Yale University pointed Dragonfly at a nearby galaxy cluster. And they saw a weird little blob. It was a faint, ghostly galaxy, a smudge. They named it NGC 1052 DF2, or DF2 for short. It was what's called an ultra-diffuse galaxy, meaning its stars are spread out over a huge area, making it very transparent. You can see the galaxies behind it right through it. They decided to study it more closely. They wanted to measure its mass to see if it too had a dark matter halo. The way you measure the mass of a galaxy like this is by looking at the things orbiting it. Just like we measure the sun's mass by looking at how fast the Earth orbits it, you can measure a galaxy's mass by looking at how fast its star clusters orbit it. These are called globular clusters, and they are ancient, dense balls of hundreds of thousands of stars. DF2 had a nice collection of these globular clusters, so the team used the giant Keck telescope in Hawaii to measure their speeds. They spent hours and hours collecting the faint light from these clusters to see how fast they were moving. And they waited for the results. The result was a total shock. The globular clusters were moving slowly. Incredibly slowly, they were moving at exactly the speed you'd expect if the only thing providing gravity was the stars in the galaxy themselves. There was no room for any dark matter, none. Maybe a tiny bit, but statistically it was consistent with zero. This was a bombshell. It was the first galaxy ever found that seemed to be missing its dark matter. The team checked their data. They rechecked it. The result held. They published their paper, and the astronomical community went wild. Many people were skeptical. It was an extraordinary claim, and extraordinary claims require extraordinary evidence. Could they have made a mistake? Maybe they got the distance to the galaxy wrong. If the galaxy was much closer than they thought, then their calculations for the mass of the stars would be wrong, and the speeds of the clusters would make more sense. The distance measurement became a huge point of contention, with different teams using different methods and getting different answers. But then Van Dokkum's team found another one, near the same area. They called it NGC 1052 DF4, or DF4. It was another one of these ghostly ultra-diffuse galaxies. They measured the speeds of its globular clusters. And they found the same thing. The clusters were moving slowly. The galaxy was missing its dark matter. Finding one could be a fluke, a measurement error, a mistake, but finding two, that starts to look like a pattern. The second discovery made the case much stronger, and since then, a handful of other candidates for dark matter-deficient galaxies have been identified by other teams using different methods. It's starting to look like these things are real, so if they are real, how is this possible? How can a galaxy form without the one ingredient we thought was essential? There are a few ideas. One thought is that these galaxies are the product of violent interactions. Maybe DF2 and DF4 pass too close to a much bigger galaxy. The intense gravity of the larger galaxy could have stripped away their dark matter halos, which are large and spread out. The stars, being more tightly packed in the center, might have been left behind. It's like the wind blowing away the fluffy part of a dandelion, leaving only the stem and seeds. This would mean they were born with dark matter, but they lost it later on. Another idea is that they formed in a really unusual way. In a high-speed collision of gas clouds, it's possible that the gas could have fragmented and formed a galaxy on its own without needing to settle into a pre-existing dark matter halo. These would be born galaxies, not made, through the slow process of pulling in matter over billions of years. They would be the exceptions that prove the rule. But the existence of these galaxies does something really profound. It pushes back against the main alternative to dark matter. You see, not everyone was sold on the dark matter idea. For decades, a minority of physicists have been arguing for a different solution. They say there isn't any missing stuff. The problem, they argue, is with our understanding of gravity itself. Maybe Newton's law of gravity and even Einstein's is just incomplete. Maybe gravity works differently on the vast scales of a galaxy. This idea is called modified Newtonian dynamics, or MOND for short. It was proposed in the 1980s by an Israeli physicist named Mordechai Milgram. The idea is simple but radical. MOND says that when gravitational acceleration gets very, very weak, like it does on the outskirts of a galaxy, gravity gets a little bit stronger than Newton's laws predict. There's a tipping point. Below a certain threshold of acceleration, the rules change. This simple change beautifully explains the flat rotation curves of galaxies. With MOND, you don't need a dark matter halo to explain why stars on the edge move so fast. They move so fast because gravity is just naturally stronger out there. It was an elegant solution. For many galaxies, MOND's predictions for their rotation speeds were actually more accurate than the predictions from dark matter models. It worked surprisingly well, but MOND has always had problems. It struggled to explain the observations of galaxy clusters like Zwicky's original findings, and it had a really hard time with the bullet cluster. In MOND, gravity is tied to the normal matter. So the center of gravity should be where the normal matter is, with that hot gas in the middle of the collision. But the lensing data shows the center of gravity is somewhere else entirely. That's a huge problem for MOND. And now, these new galaxies without dark matter have delivered what might be a fatal blow to MOND. Think about it. If MOND is correct, then the law of gravity itself is modified. It's a universal law. It should apply to every galaxy, everywhere, in the same way. Every galaxy should feel this enhanced gravity on its outskirts. There should be no exceptions. Under MOND, a galaxy cannot exist without showing this effect. A galaxy with slow-moving stars on its edge, a galaxy that appears to have no dark matter, is impossible in a MOND universe. But a galaxy without dark matter is perfectly possible in a dark matter universe. If dark matter is a real substance, a particle, then it's just stuff. And like any stuff, you can have a lot of it in one place and not a lot in another. You can imagine scenarios like tidal stripping where a galaxy could lose its dark matter. The discovery of a galaxy that seems to obey the old, unmodified laws of gravity is a huge piece of evidence against MOND. It suggests that the flat rotation curves aren't caused by a change in the law of gravity. They're caused by the presence of stuff that these weird galaxies happen to be missing. In a strange twist, finding a galaxy with no dark matter is one of the strongest pieces of evidence that dark matter is real. It shows that dark matter is a component of the universe, not a property of it. It's a feature, not the law. So what does this all mean? Where do we go from here? The discovery of galaxies like DF2 and DF4 has opened up a whole new line of inquiry. We need to find more of them. Are they common? Are they all in galaxy clusters, which would support the idea that they were stripped of their halos? Or can they be found in isolation? We also need to study the ones we found in more detail. The distance measurements are still being debated. We need to nail those down with absolute certainty. We need to understand their histories. Can we find trails of gas or stars that show they've been in a gravitational tug of war with a neighbor? And, of course, this all connects back to the biggest question of all: what is dark matter? For all our indirect evidence, we still have no idea. We've been building massive sensitive detectors deep underground, trying to catch a dark matter particle as it drifts through the Earth. So far, we've found nothing. We've been smashing particles together at the Large Hadron Collider, hoping to create a dark matter particle in the debris. So far, no luck. The nature of dark matter is one of the biggest unsolved mysteries in all of science. We know more about what it isn't than what it is. It's not made of atoms. It doesn't interact with light. It barely interacts with itself. It's some kind of new particle, something completely outside our current standard model of particle physics. Finding a galaxy that doesn't have any is a clue. A weird one, but a clue nonetheless. It helps us constrain the properties of dark matter. It tells us that the link between dark matter and normal matter isn't unbreakable. Galaxy formation must be a messier, more complicated process than we thought. It's not a simple recipe where you always add 5 parts dark matter for every 1 part normal matter. Sometimes, it seems, you can leave an ingredient out. So, could a galaxy exist without dark matter? Yes. And the fact that it can is incredibly important. It changes the nature of the conversation. Dark matter goes from being a theoretical fudge factor, an abstract concept we add to our equations to make them work, to being a tangible physical component of the cosmos, one that can be moved around, stripped away, and in some rare cases be missing entirely. The universe is always more clever and more surprising than we are. Just when we think we have a neat and tidy picture, it throws us a curveball. A ghost galaxy with no glue to hold it together. Yet, there it is. These discoveries don't give us the final answer, but they sharpen the question. They point us in new directions, and they remind us that there's still so much out there waiting to be found, hiding in plain sight. The search for what comes next is the most exciting part.